Hello everyone, this is for chapter 22 for finding confidence intervals and doing hypothesis tests with means. I thought I would use something that is currently floating around the school and tweak it a little bit and help you see how doing these confidence intervals can actually be helpful. So a certain school in Colorado wants to incentivize students to attend school by rewarding them with prom tickets if they have 5 or fewer absences during a 60-day window. Stuco needs to budget for the tickets and looks at 12 random 60-day attendance windows and finds an average of 220 students have 5 or fewer absences on average, with a standard deviation of 16.8 students. Let's find a 90% confidence interval for the number of tickets Stuco needs to pay. Well, the first thing we're going to do is we're going to say, okay, I'm doing a confidence interval. So that's straight up. I know what I'm doing. And since I'm doing a confidence interval, I have to decide if it's proportions or means. Well, since I have on average, and I have an average of 220 and a standard deviation of 16.8, that tells me that I'm working with means. So I need to do a confidence interval for means. We're going to start by pulling our data. N is 12 because that's how many samples they took. Mu, or bar x, is 220. The standard deviation of x is going to be 16.8 over the square root of 12. See, so this is what's really different is how we're going to go about finding our standard deviation. It's the population standard deviation divided by the square root of 12. And then, because I'm doing means, I'm going to need a t-star value for 90%. This is the biggest difference. Instead of doing a z value, we're going to do a t value. And remember, I want that middle 90%. So I've got 5% on both sides. That means I would look for either 0.05 or 0.95 with my calculator. Let's start by getting that. In your calculator, we're going to go to our distributions, so second vars. And in our distributions, we need that t value. So if I need a t value, I use the inverse function. So again, I either want to type in 0.05 or 0.95. I'm going to type in 0.95. And then df says degrees of freedom. Since n is 12 and degrees of freedom is n minus 1, for the t-test, my degrees of freedom is 11. So my t-star value is 1.796. Cool, easy peasy. Now, should we immediately go into the mathematics? Right, we need to check our assumptions and conditions. So let's do number 1. Each 60-day period is what? Very good, independent. Each 60-day period is what? Randomly chosen, very good. Let's use the word selected instead of chosen. It just makes it seem more, I don't know, statistic-y. Remember, 3 is where things change. We're not using NP, NQ anymore. Now we're going to go with 12 periods is less than 10% of all 60-day periods. And finally, what's the new one for means? I'm going to assume the distribution is normal or nearly normal, and 12 is enough days or enough samples. I can, now I gotta scooch up. So the next sentence starts with I. I what? I continue with n. Now what's my mean? Very good, it's 220. And then what's the standard deviation? 16.8 over the square root of 12. Good job. Sweet. So if I want to show my math for a confidence interval, it's going to be the mean plus minus my t star value times the standard deviation. And I can do my math. Then I also can use my calculator. So let's grab Mr. Calculator or Miss Calculator. We're going to go to Stat, and this is a test, so we're going to go to Test. Now, which one of these am I using? It's a confidence interval, great. So I should be looking for interval. So maybe we want to go to 7, but 7 is a z interval, which is for proportions. So I want to go down to the t interval, which is for samples. I'm going to hit enter. We're using statistics. We have a mean of 220. We have a standard deviation of 16.8. We have 12 samples, and we have a confidence level of 90%. So let's calculate this bad boy and see what we get. Oops. So I want you to pause the video and try and write the sentence first, and then start the video up again. I am 90% confident Stuco needs to buy between, okay, now remember, we're talking about people here. I can't buy part of a person's ticket. Right, so 212. So between 212 and 229 prom tickets. For students with 5 or fewer absences. Cool. Now, here's that follow-up question. And I just want you to think about this. What mistake might Stuco be making? What mistake might Stuco be making? I just want you to think about that. I can tell you we've done all the math correctly, and from the information that we have available, we have found the appropriate confidence interval and we have interpreted it correctly. But there might be some sort of fundamental error that Stuco is making where they would actually interpret this information incorrectly. Okay, so now let's look at another way to look at means. This time we're going to be thinking about a hypothesis test. Usually the average proportion of prom students who attend prom students who get ticketed during prom weekend is 6.9%. In a sample of 30 high schools in 2017, the average ticketed rate was 7.4% with a standard deviation of 2.3%. Should school officials be concerned that the ticketing rate during prom is increasing? So, how do we know that we're going to do a hypothesis test here? Because it's asking us if we should be concerned, should we feel a certain way? The question is prompting us to analyze the data and make a determination of how good or bad it is. So based on that prompt right there, to be thinking about happiness, sadness, whatever, there's a hint that you're doing a hypothesis test. You're also clearly going to compare two different rates together. The tricky part here is we're seeing rates, 6.9%, 2.3%, 7.4%. That's what we've seen in the past in our proportion testing. How do we know that this is a test of means and not a test of proportions? And it comes again to that specific word, average. Also, when you see standard deviation show up in there, your brain needs to go ding, 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 ding. I'm testing means. Let's pull the pertinent information out first. I have the rate, the current rate of 6.9%. I have my observed average at 7.4%. I took a sample of 30 schools and I have a standard deviation of 2.3%. Again, do we jump right into the math? Of course not. We do our assumptions and conditions. Condition number 1, each student is independent. Condition number 2, each school is randomly chosen. Let's see, what's number 3 again? 30 schools is less than 10% of all schools. And number 4, I assume the data is normal or nearly normal. Let's go, a little dyslexia popping there. Let's go back to number 1. Since we're talking about schools, should we be saying that the students are independent or should we be saying that the schools are independent? Because we're testing based on 30 high schools, we need to say that the schools are independent. So it's easy to get sucked into trying to figure out what is independent, what's random. Make sure they match. So I can continue with, now here's where it gets fun. Which N are you going to use? See, I got you. N is 30. N doesn't change. Which mu are you going to use? Well, obviously you're going to use both of them, right? But which one goes for our normal model? I have a normal model. My mu for my normal model is 6.9, right? But my standard deviation is going to be 2.3 over the square root of 30. Yes? Cool. So as long as we know that the distribution has a mean at our pre-known or our known average, and we're stating that our standard deviation is different, we're good to go. So where does this come in then? Where does this 7.4 come in? Just like with proportions, when we write our hypothesis test, we start with what we think is true. We think that our mean is 6.9%. But we need to test to see if the rate is increasing. So if we want to test to see if the rate is increasing, we're going to say mu is greater than 6.9%. Yes? Okay, so how does the math work? Well, we need a t star value for 30. So t star for 30 would actually be a t star of how many? 29. Very good. So we grab our happy little calculator and we go to vars and inverse. Oh, I totally lost track of what I was doing. Okay, so for this part, I'm not going to show you the math. I'm just going to show you the calculator. And we'll talk about the math in class because it gets a little sticky. Okay, so what we're going to do is we're not going to find our t star for 29. We could look that up on our table if we wanted to, but instead I want to just get to the calculation of the actual hypothesis test. So we're testing again. Which test are we going to use? See, this is where it's weird. We're going to use a t-test. And you're like, so why aren't we using a one sample t-test or something like that? Well, if we go through, we have 2 sample t-tests, and we have 2 sample intervals, and we have 1 and 2 proportion, but the only test, the only z-test, the t-test I have at my disposal is number 2. So t-test it is. And it's going to ask us to input our data. So my mu is 6.9. My observed average is 7.4 with a standard deviation of 2.3. My n is 30. So even though my degrees of freedom is 29, my n is 30. And since I want to see if it's increasing, I go for greater than. And we go down to calculate, and we get great information. Here's mu greater than 6.9. The t-value is 1.191. Our p-value is 1.217. So go ahead and try and write the paragraph. A p-value of. So there's your paragraph. What did I forget to do? I forgot to state my alpha. So if I was an actual statistician, I'd be fired. Please try and remember to do your alpha before you do your math. I know that we talk about how as long as it winds up on your assessments, you're good to go. But really, it is best if we state our alpha before doing our test. In this case, because our p-value winds up being greater than 10%, we obviously are going to fail to reject anything. So let's just set our alpha at 0.05 as usual, but just know that you really should be setting that beforehand. Bring any questions you have to class, and I will see you next period.